we are very excited to have you all today giving the talk. Let me share a couple of words about you. Since 2015, he is an assistant professor at the CS department at Technion. He received his PhD from the University of Toronto and also done a postdoc at Princeton. And his main research interests are in Boolean function analysis, computational complexity, and submolar maximization. And today he will tell us something about his recent work on end testing. Yuval, without further ado, the screen is yours. Thank you. Thank you again.
So thanks for the invitation. So this is actually joint work with a bunch of people, most of which are actually in MIT, maybe not physically, but in spirit. So there's Noam Lifshitz in Hebrew University, Dom Inso, who's he's just joined MIT this semester, and Elchanan Mosel, who's joined MIT a few years ago. Okay, so this is approximate polymorphisms. The topic is kind of a combination of property testing, Boolean function analysis, social choice theory, and maybe some other stuff, universal algebra. So the original motivation of this research is something known as judgment aggregation. Okay, so there's a kind of trial, and according to the laws of the land, the defendant is to be found guilty if they have both the means and the motive for the crime. Okay, so now we have three judges, Ehud, Shamgar, and Deborah, and we ask each of them: does the defendant have the means, what the motive, and are they guilty? Okay, so you can see here that a majority of judges thought that they have the means, a majority thought that they had the motive. Nevertheless, a majority did not think that the defendant is guilty. Okay, so this is a problem. This is known as a doctrinal paradox. Okay, this means that if you want to aggregate the opinions of judges under such rules, then using a majority vote is a bad idea. Okay, and now you can ask, okay, so maybe there's some very, very uncommon cases where when this paradox arises, but maybe if there are lots of judges and usually the votes are pretty random, that's always the assumption that they make in social choice theory, maybe then this doctrinal paradox occurs with small probability, or maybe not, if not for majority, maybe for some other function. Okay, so this is the kind of motivation that motivated Ilan Chama, whose work we improve. Okay, and as you'll see later on, there's also a property testing perspective on these things. Okay, so this talk is about approximate polymorphism. So now let me explain to you what is a polymorphism. Okay, so we're given a predicate P. Okay, this is just a subset of 0, 1 to the K. That's a Boolean predicate. And we're saying that a function f from 0, 1 to the n to 0, 1 is a polymorphism of a predicate P if the following happens. Okay, so if whenever I give you this kind of n by k table, where all the rows satisfy property P, so they belong to P, so for each such table, the following needs to happen. If I apply f to all of the columns, then this new row that has been created, it should also satisfy P. And if that happens, then we say that f is a polymorphism of P. Okay, so let me repeat it. So the setup is we have a predicate P, and we want to know which functions are polymorphisms of P. Okay, and so the predicate P is fixed, and this function f, it's on 0, 1 to the n, but actually you care about all possible n. Okay, so when is f a polymorphism of P? If whenever I take a bunch of rows belonging to P, and I apply f to each of the columns, then this new row that I get should also satisfy P. Okay, that's a definition. That's a crucial definition. So I hope you all understand it. And now we're going to see some examples. Okay. So the first example is a very famous example from social choice theory. It is said that it earned somebody a Nobel Prize. I'm not sure if that's accurate, but this is how they sometimes present it. So we have a bunch of voters, and they are ranking 3 candidates, A, B, and C. Okay, and we can record the ranking as a binary string of length 3. Now, there are only 6 possible rankings, right? 6 permutations of the 3 candidates, but a possible patterns of 3 zeros and 1s. Okay, so what's the deal? There are 2 forbidden rows. We cannot have 0, 0, 0 or 1, 1, 1, because there's no ordering in which A is better than B is better than C, or A is worse than B and worse than C and worse than A. That's impossible. Okay. So now I want to aggregate all of these votes to a single ranking of the 3 candidates. Okay, I'm not sure if there's actually any elections anywhere in the world where this is something that people do, but let's say. So we're applying this function f to each of the columns. Okay, this is known as independence of irrelevant alternatives, IIA. And this sounds like a good idea to some people.
Well,
Yeah.
so what is the function f?
Yeah, so the question is, for which functions f, is it the case that for every vote of the voters, then the outcome will always be legal? It will never be 0, 0, 0, 1, 1, 1. So that's actually a good question on it. So
Wait, so what's p? Like, is p just no everything but 0, 0, 0, 1, 1, 1?
Exactly. Yeah.
So p is like all possible strings except the all zeros and the all ones. F,
Right.
you're trying to figure out what gives you this p.
Yeah.
Yes. Okay. And
So
then
f
wait.
is a function, so that for any kind of votes, for any kind of matrix where no row is all equal, if I apply f on each of the columns, I should get another row which is not all equal.
Okay.
And now the question is, what kind of functions f satisfy this? So any ideas of any examples?
Anything but constant functions?
Okay, so actually constant functions, they don't satisfy it for technical reasons. If we allow different functions for each column, which they sometimes do in social choice theory, then it will work. But here, because of symmetry, actually, we want the functions f to be the same for all columns, and we also want them to be odd, because we don't care if it's a greater than b or b greater than a. Okay, so the focus here is on odd functions if it makes a difference. Constants definitely don't work because this will guarantee that the outcome would be illegal.
Remind me what an odd function is. A.
So an odd function is if you negate all the inputs, then the output gets negated.
Oh, okay. Okay.
Yeah, but let's not worry about this condition. I'm just looking for a function f. So if I apply it on each column, and if the matrix every row is legal, then also the new row is going to be legal. So can you think of any kind of function which, yes?
And you showed us that majority doesn't fit, right?
So majority
In your
doesn't work. I
example.
haven't shown you an example, but it doesn't work. Yeah, so you would like to do majority vote, but it doesn't work. So the question is, is there anything else you can do? But what's like, can you think of any function which satisfies this? Maybe no function satisfies this.
But it feels that function has to do something beyond only counting number of ones or zeros, because then you can always make it like 0, 0, 1, 1.
Right. So the function doesn't have to be symmetric. It can be completely arbitrary.
Mhm.
In this application, we want it to be odd, but let's forget about it. It's just an arbitrary function. We apply it on each column, we get something. And we want this promise. If all the rows are legal, then so is this outcome.
And is it allowed to also depend on the ordering of the, yes, it is, right? So
No, so I'm applying the same function on each column.
Yeah, so for
This is to
example,
be fair to the candidates. Yes, Mark?
You could output the first.
Excellent.
Bit, right?
So I could output the first row. I could also output the fifth row. Another thing I could do, which is like stupid from a social choice perspective, but I could do it. I could output the first row, but negated. Okay, this would also work. It makes no sense from the application point of view, but I can do it. So these two functions that we just said are known as dictators. So actually, it's like If I copy the first row, this means that voter number 1 decides the answer. Okay, that's why it's called a dictator. And now there's this famous theorem of Kenneth Arrow, which states that the only polymorphisms are dictators and these anti-dictators that take the what voter number 5 says and reverses it. Okay, so if you're looking for such an aggregation function that satisfies this natural axiom that the outcome is always legal, then your only choice is to point at one of the voters and let them decide. Okay, this is also sometimes known as a paradox in the social choice literature. Okay, and I think Arrow got the Nobel Prize. I'm not sure if for this theorem, but Nobel Prize in economics, so like the fake Nobel Prize. Okay, so this is one example. Now here's another example. Here the property is having even parity. Yeah.
אוי, איזה יופי. ידעתי שהיום זה טעות לבוא. סתם. כי בשנייה שהתחרתי את העלייה שלך.
Okay, so I guess it's not the question. Okay, so here's another example. So let's say that the function f is linear if f of x, x or y is equal to f of x, x or f of y for all x and y. Okay, so we all know this definition, especially if you ever studied property testing. So here's how to view it as a special case of this polymorphism setup. So here you can see x is the first column, y is the second column, and x, x or y is going to be the third column. Okay, so I'm computing the third column from the first two columns. Okay, so what is the property that all of these rows satisfy? So saying that the third column is the XOR of the first two columns is the same as saying that all the rows have even parity. That's why I'm calling it even parity. And now what is the property that the function f should satisfy? So if I apply f on each of the columns, then again, I should get that f of x plus y is equal to f of x plus f of y, which is exactly the same condition that I asked from the rows. Okay, so f is a linear function, even if it's a polymorphism of this even parity predicate. It's exactly the same thing. Yeah, this just shows that this thing that you hopefully have seen in the past, it fits this framework. Okay, so what are the polymorphisms of parity, of this even parity predicate? It's not a trick question, it's something which should be familiar. So a function f is a polymorphism of this even parity predicate if it is linear. It's the same condition. So which functions are linear? Okay, so some people in the crowd worked on linearity testing, which is the more complicated version of this question. Yeah, so what do linear functions look like?
There is a comment in chat that said inner products with subset of inputs.
Right, or the other way of stating it is just XORs of, so f is an XOR of a subset of coordinates. It's exactly the same thing. It's an inner product with a constant vector. Okay, yeah, so we all knew that. And now here's a similar example. So we're saying that f is multiplicative if f of x times y is equal to f of x times f of y. And x times y is I'm just multiplying every index, every coordinate. So xy at the position I is xi times yi. Okay, and times is the same as n because it's 0, 1. Okay, so now it's exactly the same kind of example. So here I want the third coordinate to be the end of the first two coordinates. So this is the condition that each of the rows should satisfy. And now function f is multiplicative if when I apply it to each of the columns, then again, this property holds. Okay, and in this case, the polymorphisms are going to be the 0 function, the 1 function, and also the product of any subset of coordinates. Okay, which is, you can think of it as the end of any subset of coordinates. Okay, so this is maybe something which is not as well known, but you can check. It's not hard to prove that these are the polymorphisms. So as an example, why is x1, x2 a polymorphism? Because xy1 times xy2 is the same as x1, x2, or y1, 1, 2. Okay, so I hope you could follow. If not, it should be easy to see that these products of indices, they're multiplicative because multiplication is associative and commutative. And it turns out that these are the only functions which satisfy this multiplicative property. Okay, so one final example. This is an example from combinatorics, so I think I'll skip it. So let's skip it. Oops. Okay, and now this is something which is good to know, something from the past. So if I'm going over all predicates, so for each predicate, I have the set of possible polymorphisms, or rather the set of polymorphisms. So if I go over all Boolean predicates of any arity, and for each one, I compute the set of all polymorphisms, then these things, they form a lattice. So here I put something above something else if one of them contains all the polymorphisms of the other, and I'm not sure which direction. So if you do it for all possible predicates, you get something called the post lattice. This is the same post from computability theory.
Each dot here is a different function, right? Like
it's a different set of functions. So it's a set of functions which have the same polymorphisms.
I see, and you're going to explain like how the lines.
Yes, so the lines they correspond to containment.
And what does containment mean?
So the set of polymorphisms of one function contains the set of polymorphisms of some other function.
Meaning like the functions okay, I don't.
So let's say one function only has dictators as polymorphisms, and another one has all the functions in the world as polymorphisms. So one of them would be this bottom element, and the other one would be the top element.
Okay.
And there are also things in the middle.
Okay, so it's like the functions that satisfy the polymorphism and containment. Okay, got it.
Yeah. So this is an infinite but countable lattice. And this is related. Maybe I'll have time in the end. This is related to CSPs. So if you've ever heard of Sheffer's theorem, then it's like drawing a line in post lattice between P and NP complete. Yes, so that's something which is good to know. Okay, so we will concentrate on a specific case, the truth functional setting. This is terminology from social choice theory, in which the predicate states that the last column is some specific function of the preceding columns. So, for example, we could ask that the last column is the XOR of the first two columns. This is linearity testing. We could ask that the last column is the end of the first two columns. This is end testing. Or we can do the same with majority. Okay, and for each of these cases, we ask what are the possible polymorphisms. Yes, so we always have dictators as polymorphisms. So dictator is just the function that outputs the ith coordinate. Sometimes we have also anti-dictators, which is the function that outputs the negation of the ith coordinate. Sometimes we have constant, like sometimes 0, sometimes 1. And these are known as trivial polymorphisms because they're sort of always there in one form or the other. So here the interesting question is which functions have different polymorphisms, which are not these dictators, anti-dictators, or constants. So there's a result of Dokov and Holtzman, both from the Technion. One Holtzman from mathematics, and Elad Dokov was his student, but now he's the rabbi of the Technion. Or actually, officially, he's the rabbi of the synagogue of the Technion or something. And they show that the only cases where you have surprising polymorphisms are AND and XOR. So for XOR, these surprising polymorphisms are XORs, or this inner product, as somebody here said. And in the case of AND, these surprising polymorphisms are AND. And in all other cases, you don't have anything surprising. Okay, so this will be the focus here. Okay. In the other cases, if you take a general predicate, then you get this post lattice and it gets really complicated. That's why we're focusing on this setting, which is simpler. Okay, so far we've been doing like combinatorics or universal algebra or whatever you like to call it. And now we're going to do something which is a lot closer to property testing. We're going to look at approximate polymorphisms. Okay, so an exact polymorphism, it satisfies this property that we already saw a few times. That if I give you a table and each of the rows satisfies this property P, and I apply the function f on each of the columns, and I should get a new row which satisfies this property P. And this is always, must always hold. This is a polymorphism. Now, an approximate polymorphism, as you can guess, okay, yeah, there actually may be several ways of defining it, but the way we define it is there is some kind of probability distribution on rows that this is supported on rows satisfying property P. For example, in the truth functional setting, I just choose all columns but the last one completely uniformly at random, and then I compute the last row, sorry, the last column. Okay, and with respect to this random experiment, I want that if I apply f on each of the columns, then P is satisfied with probability close to 1. Let's say 0.9, 0.99, or whatever. Okay, so it's exactly the same thing, but now I'm not asking for property P to always hold for the bottom, for the new row. It should just hold with the probability close to 1. And then I'm asking which functions f satisfy this relaxed property. Okay, and sort of the general conjecture or the, yes, question?
For the previous slide, why is the OR function not a sort of non-trivial polymorphism? If we take that,
yeah, OR and AND are the same thing.
Okay.
The same thing from our perspective. Yeah. So it's a good question. Yeah, when I said that AND and XOR, then I really meant something slightly more. Yeah. But good question. Yeah, you can also ask. You can have an AND or an OR on a subset of coordinates. It could also happen. And actually, at Dokov and Holtman, they considered a more general case where I have a different function f for each column. And then you have even more examples. Okay, so like the leading question, the motivating question behind this research is the following. Is it true that any approximate polymorphism is close to an exact polymorphism? Okay, this is really like a property testing like question. Only here we're giving the tester and we want to analyze it. Whereas usually in property testing, we're given the property and we want to design a tester. So here, just the other way around. And so the conjecture that you could probably make is that the only way to get an approximate polymorphism is to start with an exact polymorphism and add some noise. And the question is this conjecture true, or maybe there's some interesting examples? Okay, so here are some cases where we can show that this conjecture is true. Yeah.
How do you measure the similarity between?
Yeah, so I have two functions, two Boolean functions. The similarity is just the distance, like the probability that they're different.
Okay.
Yeah, it's two Boolean functions, so like all reasonable measures are the same. The important thing here is that I'm looking at the uniform distribution on 0, 1 to the n. We could look at some other distributions, some bias distribution, but and some of the results hold in this case, but kind of there's no thing, it's less well motivated. Yeah, so here are some examples. Let's ignore this NAND example. So in the case of not all equal, then we had this Arrow's theorem, which stated that the only reasonable social choice functions are dictators. And now you can ask, what if I relax this to an approximate polymorphism? So this is the same as asking, now this function f should only satisfy this property with probability 90% if the votes are random. Okay, and again, in social choice theory, people really care about random votes, and they even have a name for it. It's called impartial culture. I guess given the way that people vote in the US or even in Israel, it's actually a very good assumption. So it's a good model of reality. So can we find some other function? It's not going to be a majority, but some other aggregation function which is not dictator, and it's an approximate polymorphism if not all equal. Okay, so Gil Kalai showed that it's impossible. Every approximate polymorphism if not all equal is actually close to a dictator. Okay, in the case of even parity, then we should all know the answer. So an exact polymorphism is a linear function, which is an XOR, or this kind of inner product with the constant vector. And there's this very well-known result of Ronit with Manuel Blum and Michael Luby, that shows that every approximate polymorphism of this XOR function is actually close to an XOR. Okay, this is like property testing 101. Okay, we skip that. For the end function, and then again, we can show that any approximate polymorphism must be close to an exact polymorphism, where I remind you that the exact polymorphisms are constants or an end of rows, like a product of coordinates. And this is what we show in this work. This is what I'm going to explain to you in the remaining time. Okay, and I should say that Ilan Nechama, which is where this question comes from, he also showed a version of this. But for him, so if you start with a function which is an epsilon approximate polymorphism, so it satisfies this polymorphism property with probability 1 minus epsilon, then he shows that your function is, I don't remember exactly, but let's say n epsilon close to an end or a 0. So it's something that depends also on n. N is a number of rows. But from a property testing perspective, you want to get something which is independent of the number of rows. Okay, and this was missing from his argument, and that's where we come in. We get, for every epsilon, we get some delta, which is completely independent of epsilon. So if this approximate polymorphism property is going to be satisfied with probability 1 minus epsilon, then your function is going to be delta close to an exact polymorphism where delta only depends on epsilon. So this is what we do that Ilan Nechama does not do. Okay, so questions about that? Good. So now here's an application to property testing. So this is from a paper of Michal Parnas, Dan Aron, and Alex Morodnitsky called Testing Basic Boolean Formulae, which I date to 2002, but maybe there are also some other dates which you can find in the literature. So I'm not sure how many of you have ever heard of this. Ronit, do you know this paper?
Yes. That's it.
Okay, so at least one. So they were looking, I mean, this might be very old-fashioned, I have no idea. So they wanted to test some very basic properties like being a monomial, being a DNF, stuff like that. And in particular, here's one natural tester that they came up with for testing whether a function is a degree k monomial. So a degree k monomial is just a product of k coordinates, what we called earlier n. So what are some properties of a degree k monomial? So every monomial, it satisfies this f of xy is equal to f of x, f of y. Okay, here I'm writing n, but it's the same thing as product. And a monomial has degree k if its expectation is 2 to the minus k. And maybe the most interesting case is k equals 1. There you're doing dictatorship testing. Okay, so one way to test that f is a degree k monomial is to first sample it a few times and approximate its expectation, then seeing that it's close to 2 to the minus k, and then generate many samples of x and y and check that f of x and y is equal to f of x and f of y. So if f is a degree k monomial, then it passes both of these tests, so with high probability. Okay, so the test number 2 will always pass, but test number 1, there could be some noise. And they conjectured, but they could not show that this is also sound. That the only way to pass these tests is if you're close to a degree k monomial.
So
So
I have a question. If you took out test 1, you just take that out. Does this tell you it's a monomial?
Yeah.
Of any degree?
So that's what we show.
Oh, that's what you show. Okay, cool.
Yeah. That's what we show. So they couldn't show it. So instead, I think for the case of monomial, they also tested that the function is linear, and so for degree 1. And for the general case, I don't remember what they do, but so they find some other test but it seems that this should work, and they explained that we could not analyze this. We don't know what to do. But 20 years later, we're finally able to show that this test actually works. Yeah.
Nice.
So now, hopefully, all of us have motivation. Yeah. So, but the parameters that we get are not so nice. So, in this sense, you could hope for more, although we think that they're not optimal. Okay. So to say anything more, I'll have to do a primer on Boolean function analysis. Okay. So. Maybe some of you know something about Boolean function analysis. If not, then you'll probably be completely lost. But if you know a bit and maybe don't remember, then that will be a very short primer for some stuff that will help you understand at least most of what follows. Okay. And maybe that's a good takeaway from this entire talk, because this is Boolean function analysis is very useful, whatever you do in TCS. Okay. You never know when it's going to be useful, but even in algorithms, sometimes it's useful. And definitely in property testing and stuff like that. Okay, so there's the fundamental theorem of Boolean function analysis, and it states that every function from plus minus 1 to the n to plus minus 1 has a unique representation as a multilinear polynomial. A polynomial is multilinear if no variable appears squared or in any higher power. So if you recall earlier, we looked at functions which are 0, 1, and here they're plus minus 1, and this doesn't make a huge difference. So don't care too much about it. Okay, and this unique representation is known as the Fourier expansion. Okay, the degree of this function f, that's the definition, is the degree of the Fourier expansion. So this Fourier expansion is some kind of multivariate polynomial, and the degree of f is the degree of this polynomial. Okay, so far so good. There's this thing called the noise operator, which we'll see why it's called noise operator in I think the next slide. Here's what it does. So it's an operator that gets a function as an input and spits out a function as an output. What does it do to the function? So it writes this function as a multilinear polynomial, and then it multiplies a monomial of degree d by a factor of rho to the d. Yeah, we do it for all monomials. Okay, so this is like the syntactic definition, and there's also a semantic definition that we'll sort of see in a moment. Okay, and I'll remind you of this thing when it comes up. If you look at the expansion of f as a polynomial, then the coefficient of 1 is just the average of f, or the expectation of f. That's the same thing. Okay, and one final comment. The reason Boolean function analysis is useful is because these monomials, the different monomials that can occur in the polynomial, they're all orthogonal with respect to the uniform distribution. Here it's important that we're looking at plus minus 1 variables, because that's not true for 0, 1 variables. Okay, so I'll leave it on the screen for a few more seconds. This is, if you know all of these things, then you will be able to at least follow some of the argument, of the technical argument.
So
and if not, then there's a nice book. Yeah. Mm-hmm.
By orthogonal, you mean then they are not correlated, or they are independent?
No, so orthogonal means that they have 0 inner product, and the inner product of two functions f and g is the expected value of f times g. Okay. And the expectation is with respect to the uniform distribution. Okay, so you can think of all functions on plus minus 1 to the n as an inner product space with respect to this inner product. Inner product of f and g is the expected value of f times g. And then these monomials, they actually form an orthonormal basis. Yes, so it's also true, I think, that they're uncorrelated. And that's the same condition. So they have 0 expectations except for the one monomial, and they have 0 correlation. Yeah, this is like the reason why Fourier analysis is useful, because on the one hand, these monomials are orthogonal, and on the other hand, the monomials only depend on some of the variables. Okay, so we start with a simple example of majority. Okay, so we're going to show how to find all the polymorphisms of majority, and the same argument will actually work for approximate polymorphisms. This is the magic of Fourier analysis, that if you have a proof of the exact case, then often you can also get a proof for the approximate case. Okay, so here a polymorphism of majority is a function, so that if you apply it to each of the columns here, then you get another row with the same property, that the last coordinate is the majority of the first three coordinates. And the way to write it as a formula is like I wrote it here. So X, Y, and Z are the three columns. So on the left-hand side, this majority of Xi, Yi, Zi is the fourth column. So F gets as input the fourth column. And this is really the last element of the final row in the previous slide. That's what you see on the left-hand side. On the right-hand side, these three applications of F, these are the values of the last row on the first three columns. And the property that we're interested in is that the majority of these three values is equal to this fourth value. Okay, so I'm not sure if this was completely understandable, but it's a kind of the F and majority, they commute in a sense. Okay, this is the same condition. And we're going to write it succinctly in this form. Okay, so this is by definition a polymorphism of majority. This is equivalent to the previous definition. Okay, now here's the idea. So we fix X and we average over Y and Z. Okay, and here's what we get. So on the right-hand side, we get some kind of affine function of f of X. Okay, whatever is written here, where mu is the average of F. Okay, so to see this, you just expand majority, like you write its Fourier expansion and you compute the average. That's very easy. Now what happens on the left-hand side? So when I compute the majority of X, Y, and Z, then I get this kind of noisy version of X. So for each coordinate, there's a small probability, not so small, with probability 1/4, then I flip this value, the value of this coordinate. Okay, and the effect on the Fourier expansion is that a monomial of degree D is going to be divided by 2 to the D, which is exactly the definition of T half F. Okay, so you'll have to trust me, but that is what you get. Okay, and now really it's just a few steps to analyze a majority. Okay, so the first step, we're going to compare expectation of both sides.
Sorry,
Yes.
can you repeat? So why this is f of X if you fix X? I think I don't understand the notation.
Yeah, so I'm fixing some value of X, and I'm averaging this line above over all values of Y and Z.
Okay.
So because I fixed X and I got rid of Y and Z, then I get something that depends only on X.
Okay.
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 So now if you average over X, Y, and Z, then here's what you get. So on the left-hand side, when you take the majority of 3 random points, then you just get a random point. So the expected value of F at a random point is just the expectation of F, which is mu. And on the right-hand side, you can calculate it's this expression, this polynomial in mu. And if you solve this equation, that's very easy. Then you get that mu is either equal to 0 or to +1 or to -1. So every exact polymorphism, its average is either +-1 or 0. If it's +-1, then what does it mean? If the average of F is 1, then what is the function F?
It's a constant function?
Right, it's a constant function. So if mu is 1, then
you
F
move
is
to minus
1.
1.
Yeah, move to +-1, we'll soon move to 0, 1. So to confuse you. So if the expected value is either +1 or -1, then F is constant, okay? So the interesting case is where when mu is equal to 0.
One question. Can you remind me what
Yeah.
this T1 half thing is again? I forgot.
Yeah,
What-
so the TM1/2, you compute it in the following way. You take the Fourier expansion of f, and you divide the coefficient of any monomial of degree d by 2 to the d.
And what about it? So it's for every monomial, you see the degree and divide it by 2 to the d.
Yeah.
Not just the ones, okay, okay.
Yeah, so this Fourier expansion is a linear combination of monomials. And now the coefficients, I divide the coefficient of a monomial of degree d by 2 to the d.
Okay.
Yeah. Okay. So when mu is equal to 0, then I get the t half f is equal to half f. Because what happened when I substitute mu equal to 0. Now, what's the deal? So if you look at the coefficient of some monomial, then on the left, we get its coefficient in f divided by 2 to the d, if the monomial has degree d. On the right, we get this coefficient in f divided by 2. Okay, so how can that be? So the only non-zero coefficients have to be for the d equal to 1. Yeah. And in that case, the degree of f is 1. And actually, we know more. It's a homogeneous polynomial even. And it's known, it's very easy to show that a Boolean function of degree 1 is either constant or a dictator. Okay, so this is the entire proof that the only polymorphisms of majority are constants or dictators. It's very clean. And now, if instead of an exact polymorphism, you have an approximate polymorphism, and then everything just goes through. It's really, you put some epsilons inside and everything else, it just goes through. I mean, you'll have to trust me, but it just works. The only bit which is not obvious is now, okay, so you start with mu is now is going to be, instead of exactly 0 plus minus 1, it's going to be close to 0 plus minus 1. If it's close to plus minus 1, the function is close to plus minus 1. If it's close to 0, then we still get what we had before, but now instead of f being of degree 1, f is close to degree 1 in some sense that I'm not going to explain. Now there's a theorem, this Friedrich-Kalai-Noll theorem, that states that if f is close to degree 1, then it's close to a dictator. And actually, these people, they proved this theorem to complete the proof of Kalai's version of Arrow's theorem that we discussed previously. So this is the connection to this Arrow's theorem. Okay, so this is the entire analysis for majority. And now we'll try to mimic the same thing for end. Okay, so a polymorphism of end is a function that now it's 0, 1 to the end. So I switch back to 0, 1, just to confuse you. And the function f is a polymorphism of end if f of xy is equal to f of x times f of y. Now we're going to do exactly the same thing. We're going to fix x and average over y. And here's what we get. So on the right-hand side, we get mu times f of x, where mu is again the average value of f. Okay, this is now very easy to see. What do we get on the left-hand side? We get something. Okay, so we get the average of f of xy. The average is only over y, because we fixed x, which is it's like an average of the values of f below x. So when I multiply by y, then I possibly change a 1 to 0, but not vice versa. So we also call it a one-sided noise operator. This is something which is not so common in Boolean function analysis. And now if you wanted to mimic what we did for majority, then you would like to compare the Fourier expansions, but the effect of this T down operator on the Fourier expansion is complicated. So this won't give us anything. But here's something that we are able to do. So we can read off the Fourier expansion of this T down f from the biased Fourier expansion of f. Okay. And now I'm going to explain to you what is this biased Fourier expansion of f.
But
So
before, sorry, why do you use this operator? Why
Yes, so this operator comes up if we do exactly the same thing. We fixed x and we average over y. Then this is just what we get.
Because how do you say it? Sorry, that this is what.
So if I fix x and average over y, and I take the expectation of the left-hand side, then I get this expected value of f of xy. And this is something that I defined to be this T down operator.
Okay.
Okay, this is by definition, and this doesn't usually come up. So this notation isn't like standard or anything. So now the usual Fourier expansion is we expand any function as a linear combination of monomials, and these monomials are orthogonal with respect to the uniform distribution. So the bias Fourier expansion is the same thing, but now we choose a different basis, which is orthogonal with respect to a different measure. And where does this measure come from? So suppose we're interested in the Fourier expansion of f, and this means that we want to understand f when the input is unbiased. So unbiased, it's half-half. But then if x is like half-half, then what is x times y? If I multiply two unbiased inputs, x and y, then I get a value which is biased. It's equal to 1 in its probability only 1/4. Yeah, so if I put in an unbiased input on the right, then like on the left, I depend on these biased inputs. And this is intuitively why we need to look at this biased Fourier expansion. Okay, so this is maybe a bit vague, especially for those of you who are not versed in Boolean function analysis, which is maybe all of you. So you just have to trust me. Okay, and here we run into a problem because, okay, so you could do this, but we cannot really compare these Fourier expansions because the usual Fourier expansion is sensitive to inputs which are like around the middle of 0, 1 to the n, whereas this biased expansion mostly depends on inputs which are like a quarter to the way from the bottom of 0, 1 to the n. So it's kind of, it depends on different parts of f. So it's hard to compare them directly. So instead, we're going to do something else. This is what's in the next slide, and it's going to be maybe the most technical part of the talk.
Yuval, before you get technical on me,
yeah,
can't you just do something simple like reduce and to a majority by just hard coding half the bits to be 0, and then or am I reducing the wrong way?
So yeah, I think this goes the other way.
I see. Okay. All right. That's okay.
Yeah, but this kind of reduction, it's useful maybe for analyzing different functions. Yeah. So yeah, but this seems to be not only does it seem to be to go the wrong way, also you'd expect it to be problematic because there are more polymorphisms of majority. So they wouldn't to show up for some reason.
No, but then isn't that a reason why and should be easier? Okay, never. I'll think about it later.
I mean,
okay.
So what could
Let us
happen
have
is
it.
that maybe so you could have this reduction where you get ands as polymorphisms, and then you rule out some of them. So this is something I can understand. This is a reduction to end, but a reduction from end. So because majority doesn't have these ends as polymorphisms, it's not so clear how you'd get them if you do a reduction this way.
Okay, thanks.
Yeah, okay, so this is the technical slide, so I'll try to do it hopefully not too painful. So the starting point is this T down F operator that we defined is close to mu F. So now we're doing everything for approximate polymorphism. So that's why there's an approximation. And now the thing is here I'm going to be a bit vague. So these noise operators, they are what's known as low pass filters. Okay, so if you look at the coefficients of high degree monomials, then they will get a lot smaller. Okay, so just like this operator T half that we saw before, it divides the coefficients of degree D monomials by 2 to the D. So it really kills off the high degree monomials. The same thing happens here. Okay, and this is enough to show that our function f is close to what's known as a junta. Okay, a junta is a function depending on a few coordinates. This is the definition. And it comes from these juntas in South America. Okay, so there are some technicalities here. There's some theorem called Bourgain's junta theorem with an optimized version by Kindle, Kirchner, and O'Donnell, but let's not worry about it. The point is that we can show that this f is close to another function which depends only on a few coordinates. And now what we're going to do is we're going to assign randomly the values of the non-junta coordinates. Okay, and when we do this, then we get a triplet of functions. which are like sections of the original function f that satisfy the same kind of identity. But whereas originally we had the same function f in all three positions, now we're going to have three different functions f. Okay, so what did we do? So we wrote, we partitioned the input into f into two parts. One part corresponds to the variables that this capital F depends on. These are known as the junta variables, and the other part was the noise variables. And we can look at sections of f which correspond to fixing these non-junta variables. So there is a way to fix these variables, to fix x double prime and y double prime, so that this equation that we see here still holds approximately. Okay, so we still have something like f of x, f of y, equals f of xy, but now it's only with respect to the junta variables. And then also these sections are close to the actual junta capital F, but that's a technicality. And the point is, the thing that we gain here is that now the functions depend on only few variables, and we'll see in a moment why this is useful. What we lose here is that now instead of having a single function in all three positions, now we have three different functions. Okay, so now the point is this junta it depends on so few variables, so that the only way in which this thing can hold approximately is if it actually holds exactly, because the error is so small that it just has to be 0. Like imagine our function depends on 10 variables and the error is at most 1 over a million. Okay, and now we're basically done, because it's not so hard to show that the only way in which this kind of equality holds is if all of these functions are actually ends. Okay, and now
It's cool.
just yeah, and that's actually if you look at the paper, this is not what we do. Rather, this is something which is a lot dramatically easier than what's in the paper, and you can find it in some write-up in my homepage. So this is especially for this talk. It's quite easy and relatively clean.
Really nice.
Yeah. So I guess let's go to open questions. Yeah. So we have maybe 3 main open questions. One of them is what's the best relation between epsilon and delta? Okay. So epsilon is the probability that the test fails. And delta is how close you are to an exact polymorphism. So what we get is that 1 over delta is polylogarithmic in 1 over epsilon. Yeah, 1 over delta is polylogarithmic in 1 over epsilon. But we think that the answer is that 1 over delta should be polynomial in 1 over epsilon. Okay, but this method doesn't show it. Okay, so this is one question. Another question is to try to understand what happens for different functions. So we can now handle XOR and we can handle AND. These are the two interesting cases, like OR is the same as AND. And we can handle, let's say, majority. So what should be the case is that if you take any function which is not AND, or XOR, and then we know that the only exact polymorphisms are like trivial, what I call trivial. And it should be the case that any approximate polymorphism is close to a trivial polymorphism. So this is something we're actively working on actually right now, and we hope to show it. And maybe a third open question is this what's known as the list decoding regime. So for linearity testing, you can show something stronger than what's shown in BLR, and that's if you have a function f that passes the test, this linearity test with probability better than random, then you can obtain some structure on f. In this case, it's close to an XOR. This is for some reason known as a least decoding regime. And you can ask whether the similar statement holds for AND. And here, the threshold could be either 1/2 or 3/4, depending on what kind of statement you envision. Okay, so these are my open questions. And if you have any more questions, I'll be happy to answer.
Very nice.
Thanks.
Excellent talk.
I have questions, but maybe other people have questions first. So, okay. So I'm just curious about this polymorphism thing, because I'm not quite sure how far it extends, but I just wanted to mention there's this whole area of math called a functional equations.
Mhm.
So when I was a postdoc in Hebrew University, Nati Lineal told me, so I asked him, okay, what function classes are defined by their properties with like for alls and x, y, f of x and f of y have these things. So Nati said, go to the library and pick out this book. So I did. And there's these books in the Hebrew University Library on functional equations, and they're sort of classic books. So then so I kind of went through these books and tried to figure out which ones you could give property testers for and which ones you couldn't, or at least I was doing the best I can. So, and then, I wrote this paper and I got all kinds of because those guys didn't have email. So I started getting, a lot of real mail, like in paper from this crowd of people. So I'm just wondering whether what you've done here has anything to say about those. So let me give you a couple of examples. So first of all, the thing is, it's not going to be over, it's not over 0, 1 to the n. So you have to make some, it gets a little messy because you have to, they're always over the reals. So then, I don't know, for what I did was just assume it was over a subset of the reals and do something crazy like that. But but they have functions that look like, so basically all the trig functions satisfy what they call addition theorems. Actually, all the elliptic functions satisfy. So things like a f of x plus y equals f of x plus f of y in the numerator, and in the denominator 1 minus f of x times f of y. And that's satisfied by the tan functions. And they, all sorts of functions of elliptic functions satisfy these things. And so those are all like some relationship between f of x plus y, f of x, and f of y. So maybe that works just like the linearity test, I don't know. But they also have functions that look like f of x plus y, f of x minus y, and f of x. And they have different functions like f of x plus y times f of x minus y is equal to f of x squared minus f of y squared, things like that. I'm just wondering, if you had these weird relationships between the function values and things, is this something that would fall under polymorphisms? And is this something your techniques would apply to?
Okay, so I'm going to have several answers. So for polymorphisms, so there are at least two natural ways to consider this question. So one of them is like a non-computational way in which you really get a function on r to the n or on c to the n, and then probably you want this function to be at the very least continuous. Okay, so this is like a continuous version of this polymorphism business. I think people doing universal algebra, they usually think of the alphabet as finite. So it doesn't have to be 0, 1, but I think usually it's finite or at least countable or something. So that's from this perspective.
I'll tell you what I did. What I did was I just looked at subsets of what I did was just look at subsets that were finite, that were finite. Because these things were these functions tended to be do you know what the word I'm looking for? What happened here is what happens here.
Ooh.
Huh?
Periodic.
Yeah, that's what I meant.
Almost periodic.
That's what I meant to say.
So another answer, there's a paper, I think, of Avi and maybe some other people where they consider linearity testing where the output is not Boolean.
I mean,
okay, so this is more like what you're asking. So the technique.
that was the original linearity test was not built. Like the first 2 proofs of the linearity test was not for Boolean. The first 3 proofs. So that was for the non-Boolean case. So so because in the beginning we were thinking of program testing. And so the idea was to apply this to programs that compute more and more types of functions. So before 1996, when GGR came up with property, like we called it property testing, but we called it testing properties of, we were thinking of testing properties of programs, and we were testing properties of programs that solved more and more complicated functions. And that's why we were looking at all these different things.
But when you do self-correction, it's very important that it's actually Boolean and not real value. So maybe you have a different proof in mind. These are the only 2.
No, you can self-correct. You can self-correct.
So that's actually good to know.
Yeah.
Yeah. So, but the point is that these techniques, go ahead.
No, you can self-correct. You can. I mean, You can self-correct, yeah.
So the techniques here, at least the way I did it, okay, so for the majority function, maybe, but for the end function, we use this Bourgain's theorem, which is very specific to Boolean functions, or these two functions with a finite range. Okay, so you'll have to do something else. But from a Boolean function analysis perspective, the right question to ask, I think, is to look at functions with respect to Gaussian distributed inputs.
Okay.
And that's the kind of thing that maybe an India is working on.
Okay.
Yeah, I don't know. I'm not aware of any kind of work in this direction, but it's a very natural question. Yeah, probably rather different. Maybe the other thing is that what we're describing is usually in finite dimension. Okay.
Yeah.
I think, unless you have some examples in arbitrary dimension, and here I really are focused in usually in Boolean function analysis, even on Gaussian space, is to get dots which are independent of the dimension. So if the dimension is fixed, then usually the goals are rather different.
I see. I see.
That's a very different point of view. But yeah,
Yeah.
maybe if for example, you do what you said, you look at some kind of discretization, and you think of this as your parameter. So this is more similar to what they do in signal processing, where the dimension is fixed, but the number of samples goes to infinity. So this usually behaves very differently from what we do typically. But it's also interesting.
Yeah, no, I'm just curious because it just seemed like there would be interesting questions in just when you define a property for all statements, when can you change it to a for most statement?
Yeah.
It's really the question, right?
Yeah, right. And like maybe if you're working on real value things, maybe you want to like quantitatively measure the error. Like it's not only with hyperbolic, maybe you want to say it's a small L2 distance or something. So even maybe on most of the points it's different, but only by small amount. Yeah, you have many different variants.
Yeah, I was always trying to avoid. I was so yeah. Anyway, very nice. Other questions?
I just want to share a comment and say that it was extremely understandable talk. Really excellent one. Thanks.
Great, thanks.
So I have a small question. Do you have any relation between this and lifting by any chance? It sounds a little bit.
I must say I can't think of any kind of relation. What were you thinking about?
So very vague, nothing specific, but just the way that you break the function, right? Like a composition of function over many appearances of a different function.
Yeah. I mean,
so
that's true that this kind of composition is.
It's like the basic for lifting, right?
It's like it's also it's like the KRW conjecture. So maybe for other people, so lifting is a way to you start with a function which is hard for a simple model of computation, and you lift it into a function which is hard for a hard model of computation. So let's say you start with something difficult for query complexity, and you end up with something difficult for circuit complexity. And you do this thing using gadgets. And the way you apply these gadgets is by composition. So this is why it's a bit similar. And also in the KRW conjecture, which is a way to separate L from N or something. And also we have composition. But apart from this, I'm not seeing any direct connection. But if there is, then actually it will be very good to know. So if you think of something more concrete, then
nothing in mind so far.
Then, but like I also like lifting, so.
Yeah, I know that you worked on that before. So okay, so no connection yet. Cool.
Yeah, this function composition, you can find it in many places. You can also find it like when you do boosting to some kind of inequality, you sometimes use lifting. Composition.
And the technique of polymorphisms, was that used?
So there's something called approximate polymorphisms that is used in hardness of approximation, but it's a different notion.
I see. Okay, yeah, that was a very vague question. I agree. I just something to think about, nothing more.
Mhm.
Cool, great talk. Thanks.
Thanks.
Thank you all.
Thank you.
Okay, thank you. Thanks for your invitation.
And
Our pleasure.
And I think next week we don't have a talk, but in 2 weeks, Esti Kelman will speak to us also about Boolean functions, and it will also be at 11 a.m. or 6 p.m. Israel time. So.
Excellent.
All right. Bye.
Okay, see you. Bye bye.
Okay, see you guys. Bye.
Bye.